I'm going to speak about topological models of algebraic varieties. So the main idea is that some properties that we observe in the study of algebraic varieties, their cohomologies, maybe there are some the homotopy theory, especially motivic homotopy theory, is to some extent similar to properties of topological varieties, and their cohomologies, homotopy theory, and so on. So this is an attempt to capture some of this analogy in a more precise form. The specific aspect of this analogy will be the following. I want to consider what I call topological realization, which is a functor from some algebraic varieties or schemes into, so this is algebraic geometry, this is functor of a realization functor which I call R, and this is its image which lies in topological spaces, maybe in some sense generalized topological spaces, meaning topoi with additional structure. So I wish to make this side and this side more precise. And actually here usually we have some subcategory of the category of schemes, or, well, I can write it like this. Schemes over some base scheme S. For example, you can take algebraic varieties over some field or smooth projective algebraic varieties. Or if you are very if you want to think very generally, you can take all schemes over some ring. So what do we have on the right hand side? Here we have, so let us denote this source category by letter V. This is our category of varieties or of schemes. And here we have another category which I will denote by TE. So T is a category of spaces, and by spaces we can mean topological spaces. So it can be a topological space or the topos. And TE, E means some additional structure. So I think I have to explain what I mean by an additional structure. So, but in any case, TE is category of spaces with structure. And we have a functor from this category TE to the category T, which is the functor which forgets the additional structure and leaves only the topological space. And usually we expect this functor to be a Cartesian fibration, which essentially means that if we have an object, a diagram like this, T over T prime, downstairs, and we have an element here in the fiber, so we have an structure on the E structure on this T, then we can essentially consider the pullback of E structure from this T to this T prime. So saying that this is Cartesian fibration means that we have some notion of pullback of E structures on our spaces. So what sort of additional structures we can consider? I actually, formally, I can just define this in terms of categories, say that we have a Cartesian fibration over the category of spaces. But in practice, we want to have some examples. So examples of E. So for example, the structure may be in by taking an additional object of T over our base space X. So we have some base space X, which is belongs to our category T, and we want to describe additional structure. An example of additional structure is another object. So we can take some object AX over X in T. So in this case, category TE is just the category of arrows in T. By additional structure, we understand that we have simply a special object over our topological space X. And what kind of space it is? Well, usually it is something like an affine line over X, whatever this means. So this is how we should think about it. Another example is that we can have some map from X into some fixed space C. Well, actually, if our additional structure E admits a moduli space, then we can always take C equal to this moduli space and describe such an additional structure in terms of this a map from X to this fixed space C. So this is quite general, actually. The question is what sort of C you would like to consider. And a third example, or class of examples, is when you take some sheaf O called structural sheaf on X. And actually, in cases 1 and 3, you can require this AX over X to have some additional algebraic structure. So you can require this AX to be, for example, a relative monoid or a relative group or a relative commutative ring over X. And the same in case 3, you can just take not just a sheaf of sets O, but you can consider a sheaf of commutative rings, a local sheaf of rings, and so on. And actually, 3 is a special case of 1. Why? Because, well, everybody knows from the first works on sheaves that any sheaf can be represented by a certain topological space. I think it's called covering space associated to a sheaf, such that the fibers are exactly the fiber of sheaf, the stock of sheaf O over a point of X. And of course, you can do the same if you work not just with topological space, but with the topos. So we have topos E. Then here you have so-called local topos, E over O, which consists of just a category of sheaves with a morphism of fixed sheaf O. And this is the same construction, but for the topos case. And this allows us to reinterpret case 3 as a special subcase of case 1. So if we do such a thing, we see that we can obtain some very good topological realization if we take on the left-hand side the category of schemes, and on the right-hand side the category of locally linked topological spaces. Sorry, why do you want to consider the category of topological groups?
So, is it an example of what you understand by
addition? So, for example, you can require AX over X to be a relative group. So, a vibration in groups. So actually, of course, there is some question what we require from this functor R. So it should preserve some information about the original algebraic variety. Sometimes we can express some axioms or requirements for this R. For example, sometimes we want it to be conservative or fully faithful, so that the maps between these topological spaces with structure correspond exactly to morphisms of original algebraic varieties. Sometimes we have some cohomological conditions. For example, we can consider a tile cohomology with finite coefficients here, and want to be it to be equal to the corresponding ordinary cohomology of topological space with the same finite coefficients. Actually, I have constructed a certain list of such properties, and there are some implications between them, but I think that I don't have much time to speak about it. I think that you can already imagine what sort of properties I mean. And so we see that in this very special choice, category of schemes and category of topological spaces with a local sheaf of rings, we have a fully faithful embedding simply by definition of a scheme. So actually, a variety or a scheme is mapped into itself as a topological space with respect to the risky topology. But we think that this example is uninteresting. So this is not what we are actually looking for. Why we think that it is uninteresting? Well, the idea is that a local sheaf of rings is sort of a geometrical structure, not a topological structure. It's, of course, not a precise explanation what is when we say that a structure is geometrical or topological. But I think that the general meaning is quite clear. We want just to be able to reason about what we obtain here topologically, and if we fix a local sheaf of rings, we have to reason about its already sort of geometries, quite rigid. And so let's consider examples of. So I say that this example is uninteresting, and now I'm going to show you some interesting examples, or examples that I consider interesting. So the first example is related to an abelian geometry. So So what is this about? So this is the setup of an abelian geometry is the following. We have some field K, which is usually finitely generated over a prime field. This is a field. And we have a curve C, which is, I think, smooth over K. And its Euler characteristic is negative. The Euler characteristic is equal to 2 minus 2g minus n, so it has to be negative. N is the number of points in C in the compactification of C minus C. So sometimes people say that this is a hyperbolic curve, maybe because over the complex numbers they have a hyperbolic uniformization. So what we do with this smooth curve over K? So for example, if the genus is at least 2, then the curve is always hyperbolic. And if the genus is 0, so we have essentially a projective curve without some points, then we must have n at least 3. So we can consider a sphere without 3 points. And what we do next, we consider the étale fundamental group of this curve C. And it always fits into a short exact sequence. So it projects into étale fundamental group of spec K, which is the Galois group of spec of K bar over K. And the kernel is the étale fundamental group of the base extension of C to the algebraic closure of K. And then the idea is that the étale fundamental group or the étale fundamental group together with its projection into the Galois group of field K remembers curve C. Now you have to make this word remembers more precise. What does it mean? That a group or a morphism of groups remembers the original curve C. And usually it means results like the following. So if you have a K rational point here in C, it defines a section of this projection. And so you can ask the following question. Is it true that different rational points of C define different sections of this homomorphism? Or is it true that any section of this homomorphism corresponds to a K rational point of C? Or if you consider the category of all such curves over a fixed field K, or maybe over all finitely generated fields K, is it true that that whenever two the étale fundamental groups are isomorphic, the curves themselves are isomorphic? And actually, there are partial positive answers to these questions, maybe not for all choices of field K, but at least for some. For example, there are works of Mochizuki of 1998 or whatever, where he proves some of these results. And so I think that's what we have on the left-hand side is called, when we consider only the étale fundamental group without the projection to the Galois group, it's called absolute abelian geometry. This is called relative. So, relative abelian geometry. So, what does an abelian geometry what does it have in common with these general considerations of topological models of algebraic varieties? The idea is the following. We map the curve C here into its étale fundamental group. But actually, we can make this correspondence more topological. Just map, let's call it the abelian realization functor. It will map a curve into the classifying space of its étale fundamental group. If we are interested in relative abelian geometry, then we consider this space together with some additional structure, namely a map into fixed space called the classifying space of the Galois group of field K. So then we have a functor from the category of hyperbolic curves of a fixed field or of many fields into the category of, well, at this stage it's just homotopy types, I think, maybe with a map additional structure which is a map into some fixed homotopy type. And then we can interpret the theorems of an abelian geometry as theorems about such a functor R, whether it is conservative, fully faithful, and so on. So, is it true that if it is fully faithful, then it means exactly that homomorphisms between such groups correspond exactly to different maps of curves. At this stage, we see that we have almost obtained an example of a topological model of some algebraic varieties, but there is a problem because I wanted to have a functor into topological spaces, and at this stage, this is just a homotopy type. So, of course, we can construct a topological space which represents this homotopy type, for example, by taking a certain simplicial set and then computing the topological realization of this simplicial set. But this is it will be very huge, and it is not so it's not very canonical. And the problem will be that between such topological spaces we will have much more morphisms than we need. So we actually want only to remember the homotopy equivalence classes of maps, and we'll have a lot of maps which are not homotopy, which are homotopy equivalent to each other. So the problem here is to replace this homotopy type BG. Replace BG with a good topological representative. Another problem with this approach is that here actually the étale fundamental group and the Galois group are profinite groups, so they have some topology. And when we do this trick, replace the étale fundamental group with its classifying space, we forget about the topology. And actually, well, there are different sorts of results, but usually people still insist to consider only continuous maps here, for example, continuous sections and so on. So we have to remember the profinite topology on G. So we want to remember profinite topology So the question is whether we can do this. So for a group G, find a topological space which has homotopy type KG1 and such that the maps between such spaces are exactly the maps of corresponding homotopy types. So there are no two homotopy equivalent space maps must be equal between these representatives. And we also want these representatives of homotopy type BG to remember the profinite topology of G. So is it possible? I claim that this is indeed possible. Now I'm going to explain how we can do this. Maybe I do it here. So what is a good representative of homotopy type BG? Actually, the good representative, you cannot construct it in the category of topological spaces, but you can construct it in the category, in the topos category. So there is called classifying topos. Topos of group G. And informally, it's the following thing. You can take the point topological space or point topos. You consider the trivial G action on this point, and you take the fine quotient. Fine quotient of point by trivial action of G. And formally, what is a topos? Topos is a category of sheaves on something. And in this case, we take BG equal to the category of G sets, sets with a left excision of group G. Or you can consider your group G as a one point category with group of automorphisms equal to G, and consider sheaves of sets on this category, presheaves, I think. And this is the same thing. So if you do this trick, you can make correspond to each group G this classifying topos, and it is very small. So essentially, it has 1 point, maybe a bit less than 1 point, because you have taken quotient. My point is that if you consider the topos morphisms from BG to BH, they are in one-to-one correspondence with homotopy equivalence classes of maps from BG to BH. So if we consider this an abelian realization factor from hyperbolic curves not into the category of topological spaces, but the category of topoi, then we obtain, we can take this B pi1 et al. Of C, and we've obtained a good example of such a functor. And we had another problem. We wanted to remember the topology of group G. But here it is also possible. You can actually, if G is a profinite group, so let's denote it by G is a profinite group, then you can define the classifying topos of this profinite group, which is also denoted by BG, and it is the category of sets with continuous G action. And actually, continuous means that the stabilizer of any element of this set must be an open subgroup in this G. So it's continuous with respect to the discrete topology on this set. It's discontinuous. So, and it turns out that if we use this construction here, then such maps correspond not just to abstract group homomorphisms from G to H, but to continuous homomorphism. So you remember the topology of the fundamental group in this case. So use the classifying topos of profinite group, which is taken to be the étale fundamental group of your curve. In this way, we see that the Abelian geometry is a special case of this topological realization of some algebraic varieties, namely hyperbolic curves of some fields, into some topological spaces with additional structure, which are some topoi with maybe with maps into some fixed topos, namely the classifying space of the Galois group of the base field K. So maybe we have such maps. So this was my first example. Now I would like to make some remarks. The first remark is that why this can work only for hyperbolic curves. So why we want this Euler characteristic to be negative? This is because if it is not negative, we can have this is topologically not a K by 1, so it can have higher homotopy groups, even étale homotopy groups, and then we cannot expect this construction to remember. So the étale fundamental group doesn't remember the homotopy type, even the étale homotopy type of the curve. So we cannot expect this to work if the curve is not hyperbolic. And another remark is that actually this topos and this topos are related to the étale topos of the curve and of the spectrum of this field. Namely, the classifying topos of the Galois group of a field is exactly the same thing as the étale topos of spectrum of this field. So this is the topos of sheaves of sets with respect to étale topology on K, spec K, and this is the classifying topos of its Galois group, and they are the same thing. And here the relation is more complicated, but you can still consider the topos of the étale topos of C. So it's some category of sheaves, and inside you have locally constant sheaves. And actually, this is exactly the category of locally constant étale sheaves in here. So this is locally constant sheaves.
I think it could be called the finite étale topos.
Sorry?
The finite étale topos.
Finite étale, do you think?
The topos for the finite étale topology.
But finite étale maps will represent well, I don't understand why there, if you consider the finite étale topology, why all sheaves will be locally constant. For example, finite étale, no, I think You consider only finite italic covers, right? You want to consider only finite italic covers of C, not
Yes.
just finite italic covers of open subsets of C.
Yes, of course.
Mhm. Yes, then yes, if you consider the site of finite italic covers of C itself, then I think it works because yes. Okay, so but actually, this I want to say that this is a special case of a general construction. If you have some topos X, you can consider the category, the subcategory of locally constant sheaves inside X. And you have an embedding functor from locally constant sheaves into all sheaves, which is actually a pullback functor for a morphism, a topos morphism. Well, it's not, this thing is not always a topos, but in some cases it is. So, and fundamentally, this is the following construction. You have a large topological space, and you somehow contract it, make all points equivalent of this topological space. So sometimes it is related to operations like, I don't know, maybe X is mapped into square bracket of X. When you somehow take some topological space or algebraic variety or whatever, and in some sense or another, make all points equivalent, factorized by the complete equivalence relation. So, and this is the topos counterpart of this construction. And we see that this is exactly what we have done here with our curve C. Now, so this was my first example. So I'm going to discuss another example, which is also very interesting. So it's called the three-dimensional model of spec Z. And I think that a lot of people have been discussing such things for some time. Not a lot of people, but some people. So I think that the reference is a work by Mazur at 1964. But I think that it wasn't published. So some notes of some workshop. And later, people either retold this work or reinvented maybe independently, I don't know. And I have heard about this three-dimensional picture from Alexander Smirnov, who is here. So I hope that if I say incorrect things, that maybe it won't pass undetected. So what's this about? The original so the idea is the following: that if you study italic cohomology of, say, spec Z, spec of a algebraic number field, or of C, where C is a curve over a finite field, FQ. So italic cohomology with finite coefficients. Then you see that they behave, so they are three-dimensional, meaning that the cohomology groups H, so you study H, I, and HIC, and they turn to be 0 if I is greater than 3. So only H0, H1, H1, and H2, and H3 can be non-trivial. So in this sense, they are three-dimensional. But not only that, they behave in the same way as the cohomology groups of ordinary three-dimensional topological varieties with finite coefficients. So they have three-dimensional étale cohomology similar to singular cohomology of three-dimensional topological varieties.
I think it's called manifold.
Topological variety is called manifold. Okay, thank you. Well, actually, maybe it has some singularities, but okay, let's put manifold here. So, there was also a computation, maybe by Michael Artin and other people of this étale. There is also a paper of Mazur, I think. So there was a computation of these étale cohomology groups published a bit later without any reference to this analogy. And the general technique which is used to compute there is the class field theory. So to establish this, you have to use class field theory to compute the étale cohomology groups. And so another thing that Mazur did is that he found out. Okay, so let's just speak about the three-dimensional picture. So the three-dimensional topological manifold corresponds to, say, spec Z. And inside there are some, I don't know, it's maybe a complicated three-dimensional topological manifold. I don't know how to. And they have some submanifolds which correspond to the closed point of spec Z. So, for example, there are points corresponding to spec Fp for each prime p. And these submanifolds, they look like some nodes. So this is a node corresponding to some spec Fp. So why it is a node? So it's an embedded circle inside this three-dimensional manifold, because the étale cohomology of spectrum of a finite field is actually determined. So let's look what we have. Spec Fp étale is the classifying space of its Galois group, which is Z hat. And for finite coefficients, there is not so much difference between Z hat and Z. And then the classifying space of Z is a circle. So actually, a circle has the same cohomology with finite coefficients as the étale cohomology of spec Fp. So this is why in this three-dimensional picture, which is at this stage just informal analogy, we have some embedded nodes into a three-dimensional topological manifold. And of course, if you have a second prime, it is another node, maybe somehow entangled with this one. So this is, say, some spec FL. And people noted that so if you have several nodes inside the three manifold, you can speak whether they are entangled or not, compute some invariance of this entanglement. And it turns out that actually the entanglement depends on whether P over L is a quadratic residue or not. So actually it depends on the Hilbert symbol, I think. And actually I'm a bit imprecise here. But just let's think that and then the Gauss quadratic reciprocity law means that if this knot is entangled with this one, then this one is entangled with this. So it's very natural from this point of view. And actually people found out that so there is a certain thing in, I think it's due to Milne, in topology, when people study so-called Borromean rings. It is when you have three circles embedded into a three-dimensional sphere, such that if you remove any one of them, the corresponding two knots are not entangled. So there are two circles which are not entangled with each other. But all three together, they are non-trivial. You cannot just push them away. This is called Borromean rings. And actually, it turns out that there are some interesting invariants related to this thing, studied by Milner, I think. And there is a number theoretical counterpart of this topological construction. Maybe it's due to RDE, I don't remember exactly, but there are higher reciprocity laws for in number theory. So it's just an example where this topological analogy works in both directions, and this is rather fruitful. You can consider a topological picture and translate it back to number theory, and then you can obtain correct statements which you can prove independently. I mean, you cannot transfer the topological proof directly, but you can prove the statement by some other means. So what we want from this picture, we want it to be an example of this such a realization functor. So we would like to have a functor which transforms a spec Z into this topological manifold, and which transforms spec Fp into these circles, and the embedding of spec Fp into spec Z into this not embedding, which is drawn here. So that, and if we find such a thing, then we can just take topological results, say, about Borromean rings, and apply it to compose them with this functor and obtain number theoretical statements, for example. So it would be a very useful thing to have. So let me tell you what is what can be actually done in this respect.
But say for quadratic, is it what there's asymmetry if you look 3 and 7?
Sorry?
If there are 4k plus 3, both of them, right? So
well, it's
there's asymmetry, and in topology there's no asymmetry.
Yes, actually, there are two things that I should say. Actually, I should speak here not about the Jacobi as a Legendre symbol, but about the Hilbert symbol, which is more symmetric. And another thing is that this whole three manifold is not orientable. So there are some issues if a prime is 4k plus 1, then this this circle, we can think that it delimits a disk in some sense, maybe self-intersecting, but whatever. And if it is 4k plus 3, I think that you cannot even imagine such a thing. So it corresponds to the boundary of something that is not orientable. So it's related to the orientation of this three-dimensional manifold, actually. So you are right that.
Spec Z is not orientable.
Sorry, this manifold is not orientable. So what I want to say is to tell is whether we can make this three-dimensional model from just a vague analogy into a mathematical statement by constructing such a realization functor. So, is it possible or not? Well, the first idea how to do it is this. Just to consider the functor R et al, which maps a scheme X into its et al topos. In some sense, this is what we want, because when we compute take the cohomology of it with finite coefficients, we obtain exactly the et al cohomology of this with the same finite coefficients by tautological reasoning. I mean, the et al cohomology of X is just exactly the cohomology of X et al. So there is an obvious candidate for this functor, but actually it's not so good as it seems, and the reason is let me indicate a reason why it is not so good. So it's just an approximation of what we want. The reason is that sometimes we want to consider not just spec fp, but for example spec z over p to the kz. So this is an infinitesimal thickening of spec fp. And in this picture, we would like to obtain a tube around this, a neighborhood, I think, around this node, So, and when we take the union, so if we make k larger, this neighborhood should be larger and larger. And in the limit, we could, for example, if we take the union of them, we would obtain something that corresponds to the spectrum, well, maybe formal spectrum of Zp by taking the inductive limit. And then we can take the spec Zp and remove from it this knot which is in the middle. And if we remove it, it corresponds to localization. It should correspond to spec Qp, so the spectrum of local field. And for example, its fundamental group is the Galois group of Qp bar of Qp, so it would correspond to a decomposition group. So actually, if we want to be able to speak about decomposition groups, inertia groups, the Galois group of Q, we should have that this spec Zp corresponds to something different from spec Fp, and spec Fp is different from spec Z over p to the kz. Otherwise, some number theoretical notions would have no topological analogs. And if we want to have this, we see that the et al topology is not good for us because it cannot distinguish a scheme from the corresponding reduced scheme. So this R et al of spec Z over p to the kz equals R et al of spectrum Fp. So we need something that distinguished, that remembers the nilpotents, and the et al topology doesn't remember them. Are there any ways to do it? Well, we can, for example, consider et al topology not just on et al schemes over S, but for example over X, but consider also smooth schemes over X. So, for example, consider smooth schemes over X with et al topology, take corresponding topos, and you obtain something similar to the large et al site, but which is able to distinguish this thing from this thing. And now, if you start thinking in this direction, there is another thing that you can do, and I would like to maybe to finish with the discussion of this last thing. So maybe I should erase something like this. So I have already begun. I already began to explain that sometimes you have to consider a tile topology not just over tile schemes over X, but maybe over smooth schemes over X.
Sorry, how can you make something with hypothesis smooth scheme?
Sorry, if you have considered smooth schemes over this and over this, the categories are not equivalent, right? Because any smooth schemes can be lifted, but not uniquely. Well, a fine scheme, a fine smooth. So the last example, or maybe just not such a good example, but it's just the motivic homotopy. I'll try to explain just in a few words what I mean by this. So the idea is this, that once we have begun to consider a tile topology on smooth schemes over something, well, we might we already maybe somebody else would consider Nisnevich topology, and then consider simplicial sheaves and do some localization and obtain relative homotopy types. So actually, this is the last example of what we can have. It's just take some X and transform it to the category of motivic homotopy types over X. So these are relative motivic homotopy types. So it's quite a complicated thing to construct technically. You have, I think, to consider smooth, relatively smooth schemes over X, consider simplicial sheaves of sets, and very carefully localize the category of such sheaves by the map from the fine line cross anything to anything. So make the fine line equal to a point in this category. And then you obtain essentially what's called relative motivic homotopy types over X. Well, it's a very simplified explanation of what really goes on. And so I want to say that this is actually, it's better to consider the result not just in an ordinary category, but as an infinity category, higher category. Nobody knows whether it is an infinity topos, but actually the idea is that in this way you can obtain a functor from maybe schemes into infinity topy as defined, for example, by Jacob-Lurie. So you have to remember not just about objects and morphisms, but also equivalence between morphisms and so on. And now I maybe have just a couple of minutes to say why I think that this is the correct thing to do. So I believe that actually this might be the correct thing to do for the three-dimensional model of spec Z. Approximately for the reasons that I explained here, the tile is just not good enough. We have to do something better, which considers smooth schemes, and then this is a good candidate. And the reason why it is so good is actually a theorem due to Jacob-Lurie. So let me recall this theorem. It is from topology. So let X be a good topological space. Good, I think, means paracompact, maybe with some accountability restrictions. So all spaces that you can think of are good. and consider the category of relative homotopy types. So you consider y over x, and you consider, so this is a relative topological space over x, and you can consider relative homotopy types. So you can consider relative homotopy between maps of such things. And relative homotopy will be a map from y cross the unit interval into y prime, which is all over x. And you can take a fine, so localize very carefully by this. So you can consider topological spaces over x modulo relative homotopy. And you do, so this is what Lurie has done. He has explained this construction carefully. But basically what you obtain is the infinity category of relative homotopy types over x. And it turns out that this is exactly, so this is exactly the infinity topos corresponding to x. So what does it mean? So to any topological space, you can make you can consider the corresponding one topos. It just or the Grothendieck topos. It is the category of sheaves of sets on x, contravariant functions from open sets of x to sets. And in this theory of infinite topy developed by Lurie, you make correspond to any ordinary topological space or site the category of infinite category of sheaves of homotopy types over x. So to any open subset of x, you have a homotopy corresponds to homotopy type, and homotopy type types live in a infinity category by themselves. And you have a functor. So if you have an open subset lying in another open subset, then you have a restriction, a map from one homotopy type to another from value of sheaf on the larger. So just what you expect. You have a map from f of v to f of u, which is a morphism in this infinity category of homotopy types. And you have a gluing condition for open covers, which I will not explain here. So it's just a natural construction which embeds topological spaces into this category of infinity topy, just similar to the way the topological spaces in classical topos theory are embedded into the Grothendieck topy. So, and then it turns out that instead of considering sheaves of homotopy types on x, so this means that to any open u, you have f of the homotopy type of sections, f of u. You can do this more geometrically or topologically by considering relative topological spaces over x and taking the quotient of this category modulo relative homotopy. So what this theorem tells us, it tells us that you can actually obtain the infinite topos representative of topological space x by constructing the category, infinity category of relative homotopy types in topological sense. And of course, if you look here, you see that I suggest to do the same with algebraic varieties or schemes, but by considering the relative motivic homotopy types over this x. So if this theorem is good in topology, it tells us that in topology this is a good thing to do, consider relative homotopy types. So let's do this for in algebraic geometry in the motivic context, and then we obtain a good functor which hopefully transforms a scheme into an infinity topos which remembers most of its essential structure. So I cannot don't have any specific results in these directions. My hope is that if you do this thing, you can obtain a rigorous explanation of these three-dimensional models of spec Z, but I haven't done it yet. So I think that I stop here.